This is a proof from neutral geometry. After the time of Euclid, many mathematicians attempted to prove that Euclid's fifth axiom could be deduced from the other four. However, as we now know, this is not true. The fifth axiom is logically independent from the other four, but other mathematicians were able to prove that alternative statements were logically equivalent to Euclid's axiom 5. Previously, we've introduced one of these, Playfair's axiom, which says that given a line L and a point P not on that line, there's a unique line M which passes through the point P that is parallel to the line L. This statement is logically equivalent to Euclid's fifth axiom, meaning if we assume Playfair's axiom, we can prove Euclid's fifth axiom. If we assume Euclid's fifth axiom, we could prove Playfair's axiom. And this is, of course, in the context of neutral geometry, meaning that we're going to assume Euclid's axioms 1 through 4 hold. In this video, we're going to show another statement which is equivalent to Playfair's axiom, and this is called the similar triangle postulate, sometimes referred to as Wallace's postulate. And this basically says that similar triangles exist. In other words, given a triangle ABC and a line segment DE of any length, you can find another point F such that the triangle DEF is similar to the triangle ABC. That is, the angles correspond, A to D, B to E, and C to F. So we're going to prove that Playfair's axiom is logically equivalent to this statement, the similar triangle postulate. For the first part of this proof, we'll begin by assuming that Playfair's axiom holds, and we'll show that we can construct similar triangles of any size. So, we're given a triangle ABC and a line segment DE. Now, by Euclid's proposition 23, which only depends on axioms 1 through 4, we can create a copy of this angle alpha on the line segment DE. So we'll call this GDE, this angle equivalent to alpha. Similarly, we can create an angle equivalent to the angle at B, which I've marked as beta. We'll call that angle HED. Now, because Playfair's axiom is assumed to be true, we know that Euclid's proposition 32 on the sum of angles of a triangle is true. That is, the sum of these angles, alpha plus beta plus theta, is 180 degrees. That implies that any two angles, alpha and beta, their sum is less than 180 degrees. Therefore, these two angles being less than 180 degrees, and by Euclid's axiom 5 we know that these two lines from D to G and from E to H must intersect. We'll call that point F. At the point F, we'll call this angle phi, and because angle sums of all triangles are equal to 180 degrees, we know that alpha plus beta plus theta is equal to 180. Similarly, alpha plus beta plus phi is equal to 180. A little bit of subtraction shows us that the angle theta is equal to the angle phi, and therefore these two triangles are similar. For the second half of this logical equivalency, we'll begin by assuming that similar triangles exist and can be constructed, and we'll show that Playfair's axiom holds. So, the hypotheses of Playfair's axiom say that given a line L and a point P not on that line, that there's a unique parallel through that point. So we'll do the double perpendicular construction to obtain a parallel line. Construct a line perpendicular to L through the point P. We'll call that line K, and we'll call this point of intersection Q. Next, we'll construct a line perpendicular to K that goes through the point P. We'll call this line M. Now, in order to show that Playfair's axiom is true, we want to show that M is the unique parallel line. So assume momentarily that we have another line N passing through the point P. We'll show that any other such line N must in fact intersect L. First, choose a point R which lies on this line N, and furthermore we'll choose R to be on the same side of M as the point Q. Now we'll construct a line perpendicular to K which passes through point R. We'll call that line J. Let's call this intersection point S. Now recall that we assume we can construct similar triangles. So we have this right triangle PSR. If our given segment is PQ, we can construct a point T such that triangle PQT is similar to triangle PSR. Now because angle PQT must be a right angle, so as to be in correspondence with this angle at S, the point T must lie on the line L. Furthermore, because the angle SPR must be equal to the angle QPT, this implies that the point T must also lie on the line L. Then we have a point T that lies on both L and N. Therefore, the lines L and N intersect, so this line N was not in fact parallel to the line L. Therefore, M must truly be the unique parallel line to L passing through this point P. This completes this proof, and this also finishes the logical equivalency between the existence of similar triangles and Playfair's axiom.